Welcome to AI Frontiers, where we explore the cutting-edge advancements shaping our world. Today's episode focuses on breakthroughs in robotics research published between May 13 and May 13, 2025. We will delve into key areas such as sensor fusion, real-time processing, and human-robot interaction, which are redefining how robots perceive and interact with their environments. Additionally, we will highlight the major themes driving the future of robotics and synthesize findings from seminal papers that exemplify the state-of-the-art in this rapidly evolving field. Whether you're a researcher, practitioner, or simply curious about robotics, this episode provides insights into the transformative innovations bridging theory and practice. Robotics stands at the intersection of multiple disciplines, including mechanical engineering, artificial intelligence, and computer science. This multidisciplinary field has applications spanning healthcare, agriculture, space exploration, and disaster response. For example, robotic systems in medical settings must interpret soft tissue deformation, process information in real time, and safely interact with delicate human anatomy. These challenges underscore the complexity of designing robots for diverse environments. In recent years, there has been a notable shift from pre-programmed tasks toward adaptive and autonomous systems, driven by advances in artificial intelligence and sensor technology. This evolution marks a significant transition, enabling robotic systems to operate more effectively in dynamic and unstructured scenarios. One prominent theme in robotics research is multimodal sensor fusion, where data from different sensory modalities are combined to enhance environmental understanding. For instance, visual inertial fusion has been shown to improve hand positioning accuracy, as demonstrated in studies by Dubois et al. Another example is the alignment of tactile 3D point cloud data with natural language descriptions, enabling more nuanced robotic manipulation. These approaches reflect a growing recognition that single sensor solutions often fail to capture the complexity of real-world interactions. By integrating multiple data streams, researchers are creating systems capable of perceiving and interpreting their surroundings with greater precision and adaptability. Another critical theme is the pursuit of generalization in robotic systems. Rather than developing task-specific solutions, researchers are working toward adaptable frameworks that can perform across various scenarios and environments. Notable progress includes zero-shot learning approaches for proprioception, which demonstrate broad applicability without requiring extensive task-specific training. Additionally, contact state-aware systems, as explored by Yang et al., can interpret diverse tactile scenarios, enhancing the robot's ability to handle unpredictable situations. This shift from narrow expertise to broader competence underscores a move toward more versatile and capable robotic systems. Real-time processing and human-robot interaction represent two additional key themes in robotics research. Immediate feedback loops are essential for robotic systems operating in dynamic environments or collaborating with humans. Data-driven approaches leveraging large datasets have proven effective in improving performance, particularly in complex tasks. Furthermore, efforts to create more intuitive interfaces aim to facilitate seamless human-robot collaboration. These advancements are paving the way for robots that can integrate more naturally into human environments, enhancing their utility in applications ranging from industrial automation to assistive technologies. Recent robotics research has yielded several transformative breakthroughs. Proprioception accuracy has been improved to within 2 to 4 degrees without observable drift, marking a significant leap forward in robotic dexterity. Another milestone involves aligning tactile 3D point cloud data with natural language descriptions, advancing the field of robotic manipulation. In motion capture, tightly coupled approaches integrating inertial measurement units with multi-body dynamic models have achieved joint angle estimation accuracies of less than 4 degrees. These discoveries collectively demonstrate how incremental progress in fundamental technologies can lead to transformative changes in robotic capabilities. Several core methodologies have emerged as standard approaches in cutting-edge robotics research. Sensor fusion, which integrates visual, inertial, and tactile data, provides a more complete picture of a robot's environment. Kalman filters, particularly extended and iterated variants, enable dynamic state estimation by recursively predicting and correcting values based on incoming sensor data. Pre-trained models and sim-to-real transfer techniques accelerate development by leveraging synthetic training data that closely matches real-world conditions. These methodologies not only address current challenges but also drive further innovation, laying the foundation for increasingly sophisticated robotic systems. A seminal paper by Dubois et al. introduces novel metrics for analyzing joint coordination strategies. They developed JCV-PCA and JSV-CRP, which evaluate variations in joint contributions and temporal synchronization during movements. Using both simulated and experimental datasets, these metrics successfully differentiated between unique coordination approaches, offering meaningful insights into joint collaboration. This research advances our ability to analyze complex movement patterns, with applications in ergonomic assessments and rehabilitation monitoring. Beyond academic interest, it has the potential to revolutionize patient recovery tracking and workplace safety evaluations. Devar et al.'s work on sheet grasp exemplifies innovative hardware-software co-design for handling delicate poultry products. Their approach combines an independently actuated dual-jaw pneumatic gripper with a conditional diffusion policy controller trained from 50 multi-view teleoperation demonstrations. This system achieved a grasp and lift success rate of 40.6% and completed the pick-to-shackle cycle in 38 seconds, outperforming existing baselines. By making their CAD files, code, and datasets open source, the authors provide valuable resources for future research in agricultural engineering and robot learning, accelerating progress in automated food processing systems. Yang et al.'s investigation into real-time capable learning-based visual tool pose correction addresses challenges in minimally invasive robotic surgery. Traditional methods often lack real-time capability or struggle with generalization. To overcome these limitations, the researchers developed a vision transformer-based pose estimation approach trained via end-to-end differentiable simulation. This method enables real-time correction, demonstrating its effectiveness in simulation environments. Beyond medical applications, the study establishes a foundation for sim-to-real transferability, with potential implications for industrial and scientific tasks requiring precise tool positioning. Assessing the current state of robotics reveals remarkable progress, yet significant challenges remain. Transitioning from simulation to real-world applications continues to present difficulties, particularly in maintaining performance consistency across environments. Scaling laboratory successes for widespread industrial or commercial use often requires overcoming engineering and economic hurdles. Future directions will likely focus on enhancing adaptability and robustness, developing algorithms that require less data and computational resources, and addressing ethical considerations surrounding increased automation. As these challenges are tackled, robotics is expected to become increasingly integrated into everyday life, transforming industries from healthcare to agriculture to manufacturing. This presentation was synthesized using advanced tools, including GPT-Quen, Amazon TTS, and Grok for image generation. While the content has been reviewed by human experts, it may still contain oversights. References are provided for all cited works, ensuring transparency and accuracy. The integration of these technologies highlights the synergy between artificial intelligence and human expertise in creating informative and engaging content. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses R14.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by R14.org.